What's up? We are back. Miss Wesley here to talk some more calculus with you. And I'm at the top of page 6 of the derivatives packet where we're still thinking about derivatives, but so far we only have this first limit definition of the derivative, which is a really good way to get the derivative at a certain point. But believe it or not, there's going to be this second definition of derivative we go over today. And spoiler alert, it's going to give us the derivative everywhere at all x values. So while you're getting ready, I think the warm-up would be a good chance to see if you remember what derivatives actually mean, right? They mean instantaneous rate of change or slope of a tangent line. Why don't you get this set up, and you might want to pause the video, picturing the slopes of tangent lines at each of these lettered points and trying to decide whether you would predict them to be positive or negative. While you're getting ready to do that, of course, you would like a math joke, and I pulled it from the archives of this 101 Math Jokes book. What did the mathematician call her painting? See her with the painting? She called it, this is all in the pronunciation, she called it her masterpiece. Okay? And maybe pause now, try this warm up, and then come on back. I'll pause too. Okay, I'm back. Did you give it a try? Because if not, pause and give these a try. But can you check your answers with mine or see if you're on the same page as I am? So it says at A, it seems like the graph is falling, right? The slope of the tangent line would definitely be negative. Anytime you're at a peak or a valley, I'm thinking at B or at E, we would put 0, right? For both of those derivative values, the rate of change is 0. The slope of that tangent line is 0. I also meant for the derivative to be 0 at C, but if you had said positive, I believe I couldn't take off credit for that because of the way I drew the graph. I meant for C to be what's called an inflection point, where the graph rises, 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 levels off to 0, and then continues to rise. How'd I do on D, F, and G? I feel like the graph is rising, so positive at D, then falling at F, negative derivative value, and rising again at G. So what's with this second definition of derivative? How would we get there? Can you try number 1 using the first definition of derivative? I'm going to do the work and pause. I'd like you to pause the video, try the same thing. Let's see if we end up with the same number by the old method. So pause, okay, time in. What you see in blue here is my work using the first definition of derivative, so old news, to get a slope of a tangent line of 8 at that specific value. And you can go back and look over the work to see how that would go, but I wonder how we would find the entire derivative, the derivative at all x values by hand, like we did here. I love the calculation in blue of getting the derivative at a certain point, but what if I want a general expression that would work for all x? Here's where a second definition is going to be necessary. I mean, think about it. If we tried to use the first definition for this to find f prime of x, well, x becomes your quote-unquote c value. So you'd be finding by the first definition the limit as x approaches c, so the limit as x approaches x, that's a little weird, of what? F of x minus, it's supposed to be f of c, but we're calling that c value x, right? Over what? Over x minus c, so we call that x minus x, also looks odd. We'll end up getting, I know there's got to be a limit when it looks like I'm getting 0 over 0 with a plug-in, but I feel like the first definition is going to fail us. So in order to introduce the second definition, I want to draw a little picture. So first I'm going to draw a curve and call it f of x. I'll have it curve up through quadrant 1 like this, and I'll label it f. Let's say I care about the derivative at a certain x value. So I'm going to label it here. And on the x-axis, I'll just put the value x. And what is the y value associated with that x? Well, it's f of x. It's the output you get when you plug x in. Well, because it's weird to use the slope formula when you're at a single point, it really doesn't give you anything that makes much sense. Let's just construct what's called a secant line. I'll fill this into this blank. You can approximate the slope of a tangent line using a secant line that we're about to draw in there. I've got to pick, if using the slope formula requires a second point, I've got to pick an arbitrary point right above x. And I'm going to say it's exactly h units higher than x, and we'll nickname this x plus h. We'll bring this up to the graph here. This is just for the sake, even though what I really care about is the rate of change here, I want to use the slope formula, so I'll pick this second point that's right above it. So I'll draw the green secant line that goes through 2 points on the function. See how it's not exactly a tangent line, right? It doesn't just hit the function at one point, but its slope would be an okay approximation. And in order to use that slope formula, I need two x values. A difference in x's is going to be my denominator, and a difference in y's is my numerator. I wonder if you could figure out the labeling for this y value. If it goes x goes with f of x, well then x plus h should have an output of f of x plus h. I'm wondering if that's already ringing a bell. So let's look down here. If we want the slope of this green secant line, we need a change in y over a change in x. I'll set up, they call this a difference quotient. So it's a quotient with a difference in y's over a difference in x's, using the labeling from this graph. So the two y's are f of x plus h, that's the higher y, minus the other y, f of x. And on the bottom, I have the difference in these two expressions. They'll be x plus h minus x. They call this a difference quotient. And the numerator I'm going to leave as is, so f of x plus h minus f of x. But if we can make the denominator simpler, might as well, right? These x's should go away, and you just have an h on the bottom. This is something we're going to be using a lot when it comes to the second definition of derivative. They call it the difference quotient. I wonder though, before we get to an actual definition, I've got some pictures underneath I want to explain, but think of how this isn't a perfect slope of a tangent line, and think of how we can improve upon this calculation. Could we somehow, look how far x plus h is away from x. I feel like if we could reduce the size of h, like we still need 2 points to use the slope formula, but if we could find maybe a limit as h approaches 0, if we could find a way to make this distance right here smaller and smaller and smaller, the secant line slope should approach the actual tangent line slope. And maybe this little series of graphics might show the story a little bit better. It says, notice we have a difference quotient, and using this method, each of these pictures gives us a more and more accurate representation of the instantaneous rate of change by choosing a point apart from x, but that's closer and closer and closer to the point of tangency. Here, h is really big, right? H is a large distance, and you have this secant line. It doesn't really look much like the tangent line, but it's an okay approximation. Watch h get smaller and smaller and smaller, and as soon as h equals 0, you have the exact tangent line of the graph. So what we're going to do to this difference quotient is, I don't know if you could guess it, but we're going to put a limit on it. We're going to put a limit as h goes to 0. So we'll do that at the top of the next page. We'll say, you know what? Here goes nothing. Second definition of derivative. Here are these three probably most common ways to notate the derivative. dy dx means rate of change, first derivative. Y prime is another nickname for that, as is f prime of x. And we call this the second definition. It's the limit as h approaches 0, as that distance gets smaller and smaller and smaller, of something that comes from the slope formula, this difference quotient. So it's f of x plus h minus f of x, your difference in y's, over x plus h minus x. So how about just h on the bottom? I love using this definition, especially when you get questions like what you're going to see below, where you want the derivative at all points x. That's what it says here. It gives the slope of the tangent line at all points x comma f of x. We could find the derivative of x squared. I actually want to jump down and try these two examples. I want to look at 3. So can you set this up? Let's say we do want equations of the tangent line and maybe something called the normal line that we'll get to. But if we want the equation of a tangent line to the graph at a certain point, I think it'd be really useful to get a derivative first. Because if you recall, derivative means slope of the tangent line. So it'd be really good to have the slope of the tangent line if you're looking for the equation. So that's step 1, is let's set up the derivative. This time, since we can't really use first definition, that only works at one point, I want the derivative everywhere. Let's just practice using the second definition of derivative, limit as h approaches 0, and we've got work to do. First, we need to find f of x plus h. So what that means is, let me write it up here, f of x plus h. That means my input into this function is going to be x plus h everywhere I see x. So instead of just x squared, we write x plus h, quantity squared. Instead of just 2x, we'll put 2 times x plus h, and then it's got a 3, plus 3. All that's written in red there is f of x plus h. Then we subtract, so minus f of x, I'll be careful with signs, use parentheses, so x squared plus 2x plus 3, that's your numerator. Thank goodness your denominator is just a plain old h, not much to plug into, not much to have to simplify. So speaking of simplifying, I'm sure there's going to be an answer to this, but we've got to get rid of these parentheses so we can get there. So we will simplify. I would suggest maybe pause the video now real quick so you can take your time and try to get rid of those parentheses, and I hope a bunch of things will cancel. So I'm going to pause and we'll be right back. So I'm back, but I'm actually only part of the way through here. I have it foiled out, trying to be really careful with distributing and with signs. And this is the fun part when you see stuff start to add to 0. So 3 should go away in this calculation. X squared should add to 0, and then the 2x's. Luckily, you're left with everything in terms of h. And a little canceling here of an h everywhere should let you do the plug-in. So up top, let's pull an h out of 2xh, so you just get a 2x. We'll pull an h out of h squared, so you get an h. And then pull an h out of that 2h, so plus 2. All right. H is reduced to 1. Now direct substitution gives you 2x plus 0 for h plus 2. So here's your derivative. This is exciting stuff because it's in terms of x, and it gives you the derivative everywhere. Depending on what x value you're at, you can plug in f prime of x equals, you can plug into 2x plus 2 to get the slope of the tangent line at a given spot. So here we want the equation of the tangent line, and in this problem, we want it at x equals 2. If you want the equation of the tangent line, you need a point on the tangent line, and you need the slope of that tangent line. What's a point on the tangent line? Well, the point could just be f of 2. We could take a 2 and plug it in everywhere we see x. So we'll do that, and you end up getting, I think, 11. 4 plus 4 plus 3. So we'll say 11 for f of 2. How about the slope? Well, that's what derivative means, right? Derivative means slope of the tangent line. So we'll get used to this being f prime of 2. And that's where all this work paid off. Let's plug a 2 in for x into the derivative. And you get 2 times 2 plus 2 should just give you 6. And then if I had to pick a favorite form of the equation of a line, I like point slope form. Y minus y sub 1 equals the slope of the line m times x minus x sub 1. So plugging in here, we've got y minus, 11 was the y coordinate of the point, equals 6, and then we'll say x minus the x coordinate that we used to plug in, which was a 2. No need to simplify any further than that, and we'll skip the normal line for now. We'll just get the equation of the tangent line. I want to look at this next example and see if we can do the algebra here. So step 1 is we want the equation of the tangent line. So we will use the second definition of derivative and a difference quotient to see what we can simplify. So limit as h approaches 0, f of x plus h is 1 over x plus h minus f of x, so minus 1 over x, all over h. Okay, so to get a solution, we're going to have to combine the fractions up top. We need a common denominator. Take your time, feel free to pause. My common denominator has both parts, right, that we see here, an x and an x plus h. So giving those parts to the numerators, you will get an x, which you gave the first fraction, and an x plus h, which you'd need to give the second fraction on top and bottom. Then I'm going to pause and simplify so that we can check our work with each other and get this derivative. So I'll pause. I didn't want to get too far ahead without some explanation. You can distribute through the parentheses, and dividing by h is just like multiplying by the reciprocal. And then to my pleasant surprise, these h's will end up canceling. And you'll just get this as the derivative value. Plugging in 0 for h, it's negative 1 over x times x. Now I want to pause and see if I can find a point on the tangent line and a slope and check it with yours. So I'll pause one more time. Here goes. For the tangent line, I need a point, which is f of 2, plugging 2 into the original, 1/2. And I need the slope, which is the slope of the tangent line, plugging into the derivative. So negative 1 over 2 squared, negative 1/4. Negative 1/4 goes into the slope spot. 1/2 goes into the y1, and then I'll squeeze in the 2. Have a great day.